Okay, since there are a lot of animations, you will be clicking a lot. That's good. Okay, very good. So overview, brief history of the climate models, Detlef 2 times more, and background on emulators and where do you get them from. And then I look into a few key issues like the equivalency of SSPs and RCPs, for example, probabilistic warming and the temperature assessment that is related to the previous question that we just had. And then just briefly an outlook on the climate emulators and how they interact with EIAMs and for the future. So the past, what was done with the climate emulators in the IPCC reports is it's always the ambition is trying to coalesce to combine the working group 1 assessment for the temperature assessment of the scenarios in working group 3. And so in SAS 2000, everybody, every IAM's individual climate model was taken, was a bit of a hodgepodge. In 2007 as well, there were a few others, and then we're never quite sure whether it is actually the emission change or whether they just use different climate models so that temperatures are different. In AR5, then it was a consistent approach. There was magic taken in SR 1.5. It was also magic, but there was as well a second model that came onto the market, so to say, that is fair. And we are aiming again for a very similar approach as in the SR 1.5 approach. Next one. So here you see just what in AR5 what was done. You see there the red and gray bars, the CMAP6 models, so the big Earth system models where it takes the best supercomputers to run them, and the emulators are normally very cheap to run, only half a second, a few seconds, and that's why we run them 20 million times sometimes. So, but the yellow bars are then what we do with the emulators, and that was then done for the scenario assessment in working group 3. So next one. There's a bit of old baggage around in climate emulators. I don't mention now discussions about which should be the lowest scenarios. No, it is the old baggage that I refer to here is that simple climate models are sometimes seen as stealing a little bit of the limelight of the real big models. And that is a very legitimate concern, and that is not what we want to prolong. Therefore, we shift the terminology from simple climate models to emulators in order to emulate the big climate models and to integrate the climate system knowledge. Second, a little bit of baggage is here, as many of you will know, in the SR 1.5, we had the magic and the fair, and they were not disagreeing. They were not agreeing with each other, and at that time, there were the reasons for why they were not agreeing weren't really clear. So what we did was a big community-driven intercomparison exercise with lots of different emulators, and we did a parallel thing also within IPCC, and now that gives us now a much better understanding of why models differ. And in fact, now we have a few models that don't differ anymore because we really went down and dig deep why there were initially differences, and now they are all pretty much in line. All right, click more and once more. So background on the climate emulators, they are of varying complexity. And second part of this thing is where do you get yours from? So here, this is from 1997, the IPCC technical paper on emulators. Pretty much they have a top ocean layer, that's what they all have. They have a deep ocean, and then some of them have a downwelling pipe in order to insulate the ocean a little bit, because the ocean is really the important part here in terms of the heat inertia. So now there's a fundamental struggle that we always deal with, that climate emulators, if they get maybe the history good, they get the first 100 years okay, but then in the long term or for the very high warming scenarios, sometimes they're not providing the right response. Next slide, Detlef. That was already that one, the fundamental struggle. Next slide. So the model structures then can differ from a very simple two-layer model that can do surprisingly well, and it's really just a top ocean layer, bottom ocean layer, and that is what we will see in many publications and also in the Working Group 1 report, because it does surprisingly well for timescales up to 2100, etc. And you can go to the other end, which is, for example, a 50-layer model and with lots of gas cycles. For example, the MAGIC model is a 50-layer model. Not that every layer brings you additional gain, but that is roughly the complexity of these reduced complexity climate models. Next slide. Yep, and now you have to click a little marathon, Detlef. So you have 2 layers on the one side, click, 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 3 layers or 50 layers, and you have carbon cycles, the impulse response functions or full carbon cycles, you have other gas cycles, you have a global box or land-ocean box, you have state-dependent feedbacks or then forcing agent-dependent feedback patterns, etc., etc. So, and some of your simplest emulators are just 5 lines of code. Magic, it's 25,000 lines of code. And the at the bottom, so the key advantage, and if you want to do metric calculations, GDPs, GWPs, etc., then you want to have the increased transparency. And for some bolts and nuts and bolts, one more click, you need the a few more issues to then be really close to the system models. All right, next slide. One great place to start for you if you want to learn more about the different emulators that are on the market is the Reduced Complexity Model Intercomparison Project, rcmip.org. And here in that table, the purpose of the RCMIP is how well do they do against the CMIP6 models. And then the second one is how do they combine multiple lines of evidence. And here you see a result, the probabilistic versions in the RCMIP phase 2 for the SSP 119 scenario. The little lines in the background that you see there, they're the CMIP6 models, and then the medians are shown in that left plot. This is a temperature evolution. The red line here is MAGIC, and there are a bunch of other climate model emulators. And we do a very similar assessment, but with a bit more scrutiny even within IPCC. And here's what you saw before for the SSP 119 scenario. You see now for the other top-end scenario, SSP 585. And there you see also that many of the just 2-layer models, they're not getting all the way up to the high warming levels. And that's a known issue with having just a diffusive ocean. All right, next one. So question, Detlef also said that many of you might be interested, where do you get your climate emulator from? So there are many emulators. If you submit your scenarios, you will have probably found out to the EASA database. MAGIC is now part of the climate assessment pipeline. So your scenario will be assessed by MAGIC then automatically, and soon maybe also FAIR 1.6 or CICERO SAM that is work in the pipeline. The probabilistic AR6 consistent version will be available with the publication of the IPCC report, working group 1/working group 3. We also are going to update the web interface where you can at the moment upload your scenario. That's the old version, but that will similar feature will come then on livemagic.org in August 2021. And if you require specific interfaces for your integrated assessment model, there are API options, there are Python wrappers, etc. And contact us specifically over the next 6 to 12 months. We would be more than happy to work with you on these interfaces to update or to integrate MAGIC into your IAM. Next slide. So just briefly kicking through some key issues. The best probabilistic warming feature is not just anymore the ensemble of the big climate models. There are also other lines of evidence coming in. So therefore, that is particularly of relevance for regional climate assessments of temperature, for example, but just the ensemble is not cutting it anymore. But it's not the simple models. It's the other lines of evidence on climate sensitivity, etc., that are playing in there. Then the second issue is the non-equivalency of RCPs, SSPs. They're very close if they have the same name tag, but not quite. And then the 3 key ingredients for the temperature assessment. And one more click, Detlef. The covariance between forcings and climate uncertainties is also important. Next click. So here we have the CMIP6 models. Next click. Sorry, Detlef, here. There we have next click. And so then this is kind of more the probabilistic climate range, the assessed temperature ranges, and one more click. And that is what that probabilistic or the assessed temperature range is what the emulators try to emulate. Next slide. So here, issue 2, the SSPs tend to be a bit warmer than the RCPs for the same name tag. So if we had, for the stratospheric adjusted radiative forcing, if we had RCP 8.5 and SSP 585, then they were very, very close. However, if we go then to the effective radiative forcing, which is the forcing definition used in AR6, then, next click, they suddenly start to differ. And that's simply because the efficacy adjustments of CO2, methane, nitrous oxide, and the other driving forces, they're different. And the composition of RCP 8.5 and SSP 8.5 in the background are just different. And SSP, CO2 has something higher, methane has something lower, etc. And so then suddenly what was equivalent before in the stratospheric adjusted radiative forcing is not anymore. All right, next slide. Issue 3. The 3 key issues for your temperature assessment of your scenario is, first, you need to do the harmonization and the infilling. So click next. So if you, for example, the orange is your historical value, what you want to adjust to, then you have to do the NEROs or silicone packages. And I give the references here in the below. The slide should be shared later, so you will see the references hopefully and not that blurry bluish part there. Then next click. For your warming assessment, next click, next click, next click. For your warming assessment, the historical temperature assessment is important. So, for example, whether it was since pre-industrial to today, whether it was 0.8 or 0.9 or 1.0 degrees, and then the probabilistic emulator comes into play to exactly determine whether your scenario has a 60% chance or 50% chance to stay below 1.5 or 2 degrees. Next slide. And also the covariance is important. You can't just assume that everything like the forcings and your climate responses are independent. You need to keep the covariance into account. Otherwise, you end up with too high uncertainties and wrong results. Next slide. Okay. It's just what emulators are going to do next. There's the refinement with the new forcings, open sourcing, the probabilistic regional projections are important, especially in terms of TCFD, and then the better EIM climate model emulator integration, for example, for net negative emissions and particularly in the carbon cycle parts and also with the regional climates. And final slide, Detlef. Yeah, so if you want to have an integration, then come and talk to us. We are more than happy to collaborate with you. All right. Thank you so much.
Okay, thanks, Detlef. And in the next half an hour, we have a session on, essentially we discussed so far working group 3, we discussed working group 2, 1, and in plain IPCC language, we are now trying to bridge between working group 3 and working group 2. And so the topic of this session is essentially exploring cost and benefit. We have 2 great speakers helping us doing so. So we're going to have 2 10-minute presentations, and then we're going to have a 10-minute Q&A. So as a first speaker, I would like to introduce Kevin RENNERT, who is a fellow at the Resources for the Future. And at RFF, he has been leading, Kevin has been leading the work on the social cost of carbon, which is an important element of valuing the benefits of reducing greenhouse gases. And I will leave the floor to Kevin for 10 minutes presentation, talk about the latest RFF work on this, and rejoin just after that. Thanks.
Thank you so very much, Max, and it's you can see my screen. Okay, wonderful. Well, I'll dive in. So I'd like to acknowledge some of my collaborators on this at RFF, Cora Kingdon and Roger Cook, and my primary co-PI on this initiative is David Antoff at the University of California, Berkeley, and Lisa Reynolds out there as well. Now, RFF's Social Cost of Carbon Initiative is a collaboration primarily between RFF and UC Berkeley, but we have additional contributors from Harvard and Princeton, Duke, the University of Washington, and others. We have a science advisory board that's been stood up of a number of prominent members in the community. And our initiative seeks to really improve the scientific basis for the SCC estimates, being driven by National Academy of Sciences recommendations that were given to the US government. And in doing so, deliver a transparently updated social cost of carbon with associated uncertainty bounds. Along the way, another important contribution is that we're developing open source software tools for SEC estimation that are intended to promote transparency and serve as a common platform for SEC developments by the entire scientific community, and really to facilitate the US government's process when they now move to update the social cost of carbon. So we are implementing this full set of near-term National Academy of Sciences recommendations that were laid out in this volume, Value and Climate Damages, and these range from improving the socioeconomic projections, the climate modeling, the damage calculations, the discounting. All of these work streams have been moving in parallel and are going to come together in sort of late spring and early summer of next year. I don't have time to talk about all of them today, but we'd love to continue to engage with any of you offline about any of the other pieces of this project. So today I'm just going to give you a bit of a taste of what we're doing to improve the socioeconomic projections. Now, the socioeconomic projections for the social cost of carbon have really challenging requirements. For one, they have a very long time horizon because CO2 is very long-lived in the atmosphere, longer than a century. They need regional detail to support regional damage calculations, and they have really complicated uncertainty in that the future damages depend on improvements in technologies, mitigation policies potentially, changes in sectoral shares of the global economy, and so on. So it's a really tough set of pieces to try to put together to generate projections for estimating the SEC. So as the National Academy of Sciences wrestled with how to improve the socioeconomic projections for the SEC, they suggested that you should use statistical approaches and, when necessary, expert elicitation to replace the scenarios that were used by the federal government, the discrete scenarios, with probability densities based on a formulation of the chi identity, which sets down that emissions are defined as the product of population, GDP per capita, the energy intensity of the economy, as well as the emissions intensity of your energy. And so what they were suggesting is that we should move from this sort of set of 5 discrete scenarios that were used and averaged across for the previous estimates of the SEC by the federal government to instead laying out something that's more like this, where you have probability densities of different kind of components of the chi identity for population, economic growth, and so on. So we are implementing that recommendation, that set of recommendations, and our overarching goal is to generate multi-century projections with associated uncertainty bounds of global emissions and regional GDP and population that are also attempting to account for future policies and dependencies between the variables. It's certainly no small feat. And we're doing this for all the different components, but today I'm just going to give you a window into the work we've been doing specifically on the economic growth projections to give you a sense of what the work stream has been like. So the work that we're doing to generate the economic growth projections in this sort of probability density format is a 3-step process. The first, we are projecting country level economic growth using an econometric model. The second is we are quantifying expert uncertainty about that future economic growth. And the third is we're constraining the econometric projections with that combined expert uncertainty. And so at the end of this, the idea is to have country level projections of economic growth that are running very far into the future, but are incorporating the benefits of both the econometric approaches and the expert approaches as well. So in that first step, the econometric model we're using was put forward by Ulrich Mueller and Jim Stock and Mark Watson as a Bayesian hierarchical model for the frontier of growth and country-specific deviations from that frontier. And each of the 2,000 trajectories that come out from that model provide a central OECD growth path that I've shown here. I'm just showing one illustrative example of a draw from this model, along with each country's deviation from that path, which yields each country's projection. So as you see this is just one of the 2,000 draws from the model. The blue is the OECD again, and the gray are the individual countries' deviations from that OECD growth path. So that actually by itself gives you the country level projections we're looking for that run all the way out into the year 2300. The Academy was very clear that using a statistical model and running it just kind of as far arbitrarily into the future has some real concerns associated with it in terms of going well beyond your the historical record that the statistical model is trained on. And so they suggested incorporating expert judgments in a very formal fashion. So we designed an expert survey that was really intended to be used in tandem with these econometric projections. This is the RFF Economic Growth Survey that we actually concluded even before the pandemic started, but we are now finally in the process of getting it fully written up, where we surveyed 10 leading growth experts individually over 2-hour Zoom sessions. We were doing Zoom before it was cool. Where each expert provided median and 90% range on a set of calibration questions for which the true values are actually known. And doing these calibration questions gives you the opportunity to performance weight the experts in the combination. So you can have both an equal weight combination of experts distributions as well as a performance weighted distribution, which has been shown to provide a number of advantages. After the calibration step, then each expert was asked to provide their first, 5th, 50th, 95th, and 99th quantiles of OECD GDP per capita for a set of years all the way out to the year 2300. To give you a sense of what this looked like from the experts, we show you the survey results over the average growth rates of OECD GDP per capita from 2015 to the year indicated in the top of the graph here. So our the gray bars here are each represent an individual expert, whereas the blue and the red represent the equal weight combinations and the performance weighted combinations, respectively. As you look at the gray bars, obviously you see a number of things stand out. One is that there is a fair bit of deviation between where some of the experts are in terms of their extreme uncertainty. You also see that generally the experts feel like the economic growth, even from 2015 to 2050, falls more in the kind of range of 1% to 2% on average. And if you look out over time to 2100, 2200, 2300, you see that actually overall the experts generally tend to believe that that's economic growth in the recent historical record is not going to be sustained for the long term. And the median is actually lower than where you might get with a statistical approach. So that was step 2 with the economic growth survey. And step 3 is to combine that with the econometric approach. So our goal here is to preserve those country level correlations that are provided by that model, but quantify some of them and inform it based on the expert judgment. So the method we used was to use iterative proportion fitting to assign new probabilities to each of the trajectories provided by the MSDO approach to achieve the constraints on the quantiles of growth. So effectively, the estimates of the SEC are calculated over time. So in summary, we're writing this up right now, so also please do not cite, but the econometric and expert projections indicate a similar range of overall uncertainty in economic growth, with the experts projecting a lower median of growth in the statistical approach. The uncertainty range suggested by both of those approaches is greater than spanned by scenarios that are typically used for assessing climate change and climate damages. It's absolutely much wider than what was used by the federal government as it was assessing its own sociocultural carbon, but also wider than provided by, for example, the SSPs. When you try to use this new distribution of growth, it also highlights the need that you really need to update the other components of socioeconomics as well, in particular the emissions intensity assumptions and the damage function formulations. And we are doing all of this as a part of the initiative. So I'll conclude with talking a bit about the other important contribution of this project, which is the software platform. It's referred to as the MEINSHAUSEN framework. And this is a software platform that was developed by David Antoff. He's leading this project as an open source. It's open source on GitHub. It's been implemented in the Julia programming language as a registered Julia package. The idea is that it's providing an accessible and easy to use interface for building and running integrated assessment models. The focus of MEIMI is really on readability, so that it's very straightforward for scientists that are not necessarily integrated assessment modelers to be making contributions by really focusing on just the pieces that they need to in terms of the science that they're trying to implement, and not having to worry about really the behind the scenes plumbing that is putting everything together and making it run. MEIMI delivers on the National Academy's recommendation to unbundle and modularize the steps of SEC estimation, where what the Academy was envisioning was that instead of having kind of closed models, you could have a model where you could easily swap out, say, a damage formulation or swap out an entire climate model and have them all running in sort of compatible fashion. It also, despite its focus on simplicity, provides support for some more advanced features such as Monte Carlo simulations and Sobel analysis. So please check out mimiframework.org for more of this. And I would close by saying that MEIMI is already very full-featured. It has a number of models and components already available. It has, in terms of integrated assessment models, it has FUND, it has all the versions of DICE, it has RICE plus AIR. It's the only fully open source, I think, implementation of Page 2009, and Page ICE is now being developed on MEIMI. There are a number of different climate models and physical science components such as FAIR, SNEEZY, Hector, CM, BRIC, NICE, AWASH. So it's really become a very vibrant community, and we're expecting it to get a lot of traction as the US government moves to update their estimates as well. And we look forward to engaging with all of you on it. So with that, I'll conclude, and thank you very much, and I look forward to the Q&A.
Kevin, That was really great. Move to our next speaker. Laurent DROUET is a senior scientist at the European Institute on Economics and the Environment, which is a collaboration also including resources for the future. And Laurent will be report to us on the latest community work on impacts, integrating impacts and mitigation.
Okay, thank you. Can you hear me? Yes.
Yes.
Okay, thank you. Hi everyone, my name is Laurent DROUET. I am a researcher at the RFF-CMCC European Institute on Economics and the Environment. Today I'm going to talk about the benefits from mitigation in integrated assessment models. So the cost of mitigation are still one of the main outcome of integrated assessment models. They have been reviewed in the last IPCC report and also in various studies. So here I show two plots which relate the mitigation cost estimate from IAMs with the policy stringency. What we can see is that the more stringent the policy is, the higher is the cost, but also the most uncertain. But it gives only a partial view of the implication of mitigation, as the ultimate goal of mitigation is to limit global warming, and in consequence, it's to reduce the impact of climate change. So this reduction is indeed the benefit from mitigation. So how can we get these benefits from mitigation? Well, this is simple. We need to project the impacts of climate change for two scenarios, and the benefits are the difference between the impacts in these two scenarios. In particular, if we can compare the impacts in a baseline scenario where no policy occurs with the impacts in a policy scenario, for example, RCP scenario. Or we can also compute the benefits to transition from one level of mitigation to another, for example, between 2 degrees and 1.5 degree scenarios, or also between scenario design. So for an integrated assessment model, this would require to evaluate the climate change impact for different development of pathways. So some impacts, the geophysical impact, they are estimated from outcomes from GCM, height resolution scale. And these impacts can be compared with different emission scenarios. And they are usually based on the RCP or the SSP RCP framework. So this is what has been done in numerous studies, but it manages a large amount of information. It's difficult to directly link with emission pathways that are generated by IAMs directly. So hopefully there are some studies that summarize the information, highly detailed information on impacts under the form of regional damage function that we can use, and then this function relates the global temperature increase with a set of impacts. For example, using the illustration at the bottom, an example of one of these impact function here from Arnell et al. 2019. And then you have a different, what is interesting is that you have different impact function for each GCM. And then you can see on the right, the distribution of impacts you get from the ensemble of a climate model. And usually these functions, they are monotonous increasing, but the shape is changing according to the impacts, going from very linear to very steep and logistic function. Concerning the economic impacts, there are recently a growing literature that produce a lot of new estimates. However, these estimates are vary widely and depend considerably on the methodology which has been used to produce them. So in a perspective paper, which is still under review, which is led by Francisca Ponte, these estimates have been categorized to ease a bit the use of them and to be able to select them for our purpose. So some estimates, they come from some bottom-up assessments by adding up the impacts per sector, and some other, they come from top-down assessment. You have a lot of diversity and also disagreement between the studies. So it's somehow necessary to select more than one damage function when you want to assess impacts and benefits from mitigations. So now I will talk about the multimodal comparison exercise that is currently happening in the Engage project. It involves 9 integrated assessment models that you could see the list on the left. And they produce emission pathways that are compatible with more than 10 carbon budgets. So a very high level of granularity here, which spans the space of long-term climate targets. And for each of the carbon budget, the model implements two types of scenario design. One scenario design, which is called the full century carbon budget, which is the standard implementation of carbon budget with a global carbon tax, but also a scenario design, which is called peak temperature budget, which doesn't allow for net negative emissions. So you stay at zero net negative emissions. So basically you limit the use of negative emission. And also the advantage of this scenario that you avoid an overshoot and then the temperature is stabilizing. But another interesting feature in this scenario design that they lead to the same temperature in 2100. So basically you have the same endpoint. So with this wealth of models, we can try to see what is the influence of the carbon budget or the scenario design on the impacts. So looking at the geophysical impacts, I show here 3 impacts that are related to extreme heat. We can compare the distribution for low temperature target on the left to high, which is here 2 degrees higher level on the right. But you can also compare the two types of scenario design, which are here the color of the distribution. So the primary influence is really temperature target. You see a clear difference between the two distribution on the right and the left. But you can see that going from a full scenario design to a peak scenario design, that shifts the distribution towards lower level, which means that basically you will remove a bit of the risk, especially that if you look at the tail of the distribution, the upper tail is getting fatter for the full century budget. About economic benefits from not overshooting, so comparing the economic impact between the two color scenario design, we apply here 2 different damage functions. So on the top, the growth-based damage function from Vuuren et al. 2015, where the impacts are accumulating over time and the damages are persistent. So in this case, the benefits of avoided damages are large and they increase all over the century. In the second row, there are the benefits where we apply a level-based damage function, which is based on the award on Sterner 2017. In this case, the benefits, they are increasing and decreasing following a bit the gap of temperature between the two scenarios, because in this case, the damages are not persistent. So with this example, we see that economic benefits are highly influenced by the way climate damages are, economic damages are represented in the model. So I will finish this presentation with some recommendations that come from the perspective paper led by Francisca Piontek. So the recent development from literature and impact have been already included or are ongoing in some integrated assessment model, but still there are some questions about the use of these impacts because of some problems that I highlight here. So the degree of persistence of damages, the effect of adaptation, some they have no adaptation, some they use current technology. If we can apply these estimates, especially the empirical estimates, to do future projection, or if we have to be careful with this. And then also, of course, the still missing impact channel that are not present in these estimates. So to do this, we really need to do sensitivity analysis using different damage function. And in the second part, integrated assessment model, they should be improved structurally to deal with the impacts. So by having higher spatial and socio-economic resolution, to be able to capture the distributional effect, the heterogeneity in impacts. Also, they should account for the cost of adaptation, the measure of adaptation. And also, maybe they could be modified to directly include some biophysical model outputs. So basically, you pass through this reduced form damage function, if it's possible. So for that, good progress could be made with the help of intermodal comparison exercise, with a focus, a special focus on impacts and the benefits of mitigation. Thank you.
Thanks to both speakers. I would invite both Kevin and Laurent to stay on and click. Kevin, you can click the green button to come back in the plenary, and and for Q&A, let's start Q&A session. I see questions for Kevin so far. Please keep writing them in the chat. It's a bit complicated because depending on how many likes you get, it's going to move up and down. But Kevin, we have questions for you, a couple of questions for you first. What about disruptions such as the pandemics? I guess everyone is asking. To what extent do you think that would change the picture, which is a very long-term picture, but nonetheless would influence your estimates of GDP growth? And to what extent, second question, the assumptions and the calculations by the experts and your assessments account also for direct impacts of climate change and environmental stress on growth, which both could be limiting factor in economic growth?
Absolutely, those are both great questions. So to take the first one, it's sort of fascinating. We concluded the survey well in advance of the start of this pandemic, but we asked the experts to think about disruptions that they could imagine in their projections of long-term economic growth. And generally, the response that we were getting from the experts in the dialogue was, we feel that there will be disruptions, certainly, but that as you're looking in the long term, that those types of disruptions will generally be smoothed out. And the longer you're looking into the future, the more time there is really for recovery and for a general responding, getting back on track from disruptions like that. We asked them specifically to actually highlight their top sort of three factors in lower economic growth, and a number of them actually did suggest that pandemics might be one of their top three to really impede economic growth. So I found that quite prescient. In terms of the other, we asked them to think about the economic growth projections in the absence of climate damages, because you want the models to be able to actually be calculating those damages. You don't want to be double counting. But we then also went back and asked them to think about sort of the amount of climate damages and how that would affect their projections in general. And generally, they found themselves feeling like of all of the different factors, climate change and climate damages would certainly be one of the most pressing, but that with all the uncertainty, it wouldn't substantially change their actual quantification of the uncertainty of economic growth moving forward. And so you can sort of use it in both of those contexts.
Question is about the interaction terms, between the different terms of the Chi identity, which you just outlined. Clearly, certain economic growth patterns are related to certain capacity to mitigate and to emit. And to what extent are you taking these correlations into account in your framework?
Yeah, that's a great question as well. And so, so the way that we've been approaching this is actually, as we've sort of worked our way through the Chi identity and keeping all this in mind, with the emissions intensity piece, the carbon intensity that we're kind of currently going through. The intent is to have that elicitation that we'll be doing with the experts to be conditioned on kind of a bucket of economic growth. So if you're in a high economic growth kind of framework, if you're in a medium economic growth, or if you're in a low economic growth framework, and then have the carbon intensity itself be getting different distributions from the experts in terms of their uncertainties related to where you are in terms of the economic growth pattern. So this is a bit of a crude way of trying to condition things like the Chi identity terms on each other. But when you're dealing with things like this is, I think, the most appropriate way we can go about it in terms of accounting for those.
Questions about the MIMI framework, whether it is suitable for optimization or it's just meant at simulation models.
So it is not currently set up for optimization, but that does not mean that it could not be in the future. I would direct questions like this to David Antoff, who is the really the expert on all these. But yes, it certainly is. It's quite a full-featured piece of software.
And Laurent, what do you think, in relation to Malte's presentation before, can be the role of reduced complexity models in analyzing the work that you just described, and especially when it comes to projecting things which matter for impacts which are not just temperature, but temperature variation and extremes, as you show in your drought charts, or even sea level rise, if looking far into the future.
Yes, of course. I mean, the global mean temperature is an interesting indicator, and this is done well by the climate emulator. But it would be interesting that the climate emulator is also looking at the extreme values, and even can go a bit beyond the physical values, like providing some impact indicators. I think just one step forward that is exactly doing the climate model. But that would be very interesting because if the model is calibrating in the same way for all these geophysical variables and impact variables, that would be very helpful to have consistent information to be used. Also, I mean, of course, at a regional level.
Where, in terms of co-benefits, something which you didn't discuss, but that the community has been done a lot of work on,
yes.
such as air pollution. To what extent the integration with the air pollution projection is also important here.
Yes, this is important, and in fact, it's very similar. It's more like you will compare, when you look at benefits in that direction, you will compare basically the no policy case against policy case, and then you will get a value that you can compare with the cost somehow. While with the co-benefits, you will look at the trajectory and if you can. So maybe this is more. I mean, both are interesting, but it's maybe they can answer different questions when you want to select emission pathways, also feasibility of emission pathways.
By the paper led by Francisca Piontek, of which you are co-author, it's about to what extent the damage functions were fitted across studies, in the sense that there are studies depending on whether they look at growth effects, essentially depending on the persistence of the impacts. The studies, of course, lead to relatively rather different conclusions. And so, how can those be reconciled?
That's a big question, and I think that's why we have to be very careful to understand how these numbers have been produced, and not to combine them without looking at the all assumption. So I think this is, for example, the paper from Howard and Steiner did this, but for just one type of estimates. But for other estimates, yeah, you have to be very careful and not combining. So I would go rather for using different damage function and do more like some ambiguity analysis.
In a way, bringing back to what Kevin introduced, the importance of assessing uncertainties, and also in the importance of combining empirical work, either from historical data or from experts, to inform our future understanding of the future climate and its impact. So I would thank both speakers for this great session, short but great.